we're going to be wading further into terminology regarding graphs. So we've already remarked that any graph can be considered isomorphic to itself by the identity map. But that doesn't mean that's the only isomorphism from a graph to itself. Maybe there is another way to bijectively map the vertices of a graph to themselves that actually preserves edge structure. Maybe there are other isomorphisms from one graph to itself. Anytime you have an isomorphism from a graph to itself, it's called an automorphism, a self-morphism of the graph. So automorphisms represent ways that the labels on the vertices and edges could kind of be permuted around, but not changing any of the underlying structure of the graph. The bijection from the vertices to themselves, that's a permutation. The bijection from the edges to themselves, that's a permutation. So you're permuting the labels on the vertices and edges. Since it has to be an isomorphism of graphs, if two vertices are connected by an edge and you move the labels around, you're preserving which edges are connecting which vertices. But somehow, none of the underlying structure is changing. If a graph has the property that for any two vertices that are connected, so pick any two vertices in the graph and see that if they are connected by an edge, there happens to be one of these automorphisms that switches those two vertices. So anytime two vertices are connected by an edge, it's possible to switch them with an isomorphism. Then the graph is called symmetric. And an automorphism that switches those vertices is called a symmetry. So these definitions hold identically whether you're talking about simple graphs versus multigraphs, directed versus undirected graphs. All of these definitions are the same. We tend to just draw simple undirected graphs, but none of the terminology really changes. So in short, if you have a symmetry of a graph, what you have is an automorphism of a graph, in other words, an isomorphism from a graph to itself, which switches one specific pair of adjacent vertices, two connected vertices. And provided that such an automorphism exists for every pair of adjacent vertices. It's possible, by the way, to have a single automorphism that switches one pair of adjacent vertices, but not have it be possible for all of them. You only invoke the terminology of symmetry when for any pair of adjacent vertices, it's possible to switch them via an automorphism. Of course, examples are very helpful in illustrating these ideas. So let's show that the graph here is symmetric, and we will give three symmetries of it. Now, we are not just talking about looking at the graph and describing visually how the symmetries are described, because we're not talking about how we draw the graph. Symmetries in graphs are defined in terms of automorphisms, which is a bijection between vertex sets and edge sets, not anything about how we draw it. Well, there are three vertices in this graph that are all connected to one another. If a graph is symmetric, then for any pair of connected vertices like A and B, there must be an automorphism that switches these two vertices. So since I have three connections here, three edges, okay, define three different pairs of connected vertices. Out of the three vertices, I can choose any two. So there are three choose two, which is just three, different possible symmetries that I need to describe, one for every edge. Okay. Remember, a symmetry has to switch two vertices connected by an edge. Since to call the graph symmetric, I need to be able to do this for any two connected vertices. What I need to do is come up with an automorphism for every edge. Okay, so we will construct a symmetry for each choice, and then we will show that those are the only possible symmetries. So for example, consider vertices A and B, which are connected by this edge. What we need to do is come up with an isomorphism of this graph to itself, in other words, an automorphism, that swaps these two edges. So f of A had better be B, and f of B had better be A. Well, since A got mapped to B and B got mapped to A, the only choice is for C to stay where it is. The edge connecting A and B, well, A went here and B went here, so this edge can stay where it was. The edge that used to connect A and C, since A got moved to this location, had better be mapped onto the edge connecting B and C, which we have here. And since B was connected to C down here, but B got moved up to this corner, it has to get mapped to the edge connecting A and C. And there we have it. So what we have here is a bijection between the vertex sets and the edge sets. And since A goes to B, B goes to A, C goes to C, we see that all of these edges preserve those connections. Okay, so it does take a little bit of checking, but this is a bijection between vertices and edges that preserves connections, so it's an isomorphism. It's an isomorphism from a graph to itself, so it's an automorphism. And it swaps the edges A and B, so it's a symmetry on that edge. Okay, so once we picked a couple of things, a lot of pieces fell into place, but we were able to construct a symmetry, specifically a symmetry that swaps vertices A and B, or a symmetry of the edge connecting A and B. So what we did on this graph is we mapped the vertices to themselves to switch the vertices A and B. Once we switch the vertices A and B, because there's only 3 vertices, C was locked in itself. Since these 2 vertices got switched, these 2 edges got switched, but this one had to stay where it was. Okay, notice in any symmetry, the 2 edges that you switch, the edge connecting them will just stay the same, but other stuff might not start moving around. In this case, these 2 edges had to get switched because we switched these 2 vertices. This edge had to stay where it was because it was the edge of symmetry that we were using. So once we declared we were swapping the vertices A and B, there was no other choice. This vertex had to stay where it was, and the edges were now declared. So that's the only possible isomorphism of this graph to itself, in other words, automorphism, that swaps the vertices A and B. So you can go through similar arguments to show that for any other pair of vertices, like A and C, or B and C, there's only one way to construct an automorphism of the graph that swaps those 2 vertices. Since there's only 3 edges, what we've shown is there are 3 symmetries of the graph and no more. One more example will help illustrate these definitions further. We're going to show that a specific graph is not symmetric, and the way we're going to do that is by arguing it is simply not possible to find an automorphism for one specific pair of vertices. Now here's the graph. For vertices A and B, we're going to show that there is no possible automorphism that switches them. In a symmetric graph, automorphisms are really only required to switch 2 vertices that are connected by an edge. So I wouldn't ask, for example, to find an automorphism that switches vertices B and D because they're just not connected to each other. A and B are, however, so if this graph is symmetric, there must be an automorphism that switches them. So if we can show there is no automorphism that switches them, then this graph is not symmetric. Well, automorphisms, being isomorphisms, have to preserve edge relationships. Therefore, they have to preserve degrees. We've already argued that if 2 graphs are isomorphic, a vertex of a given degree has to be mapped to a vertex of the same degree. That doesn't change just because we're talking about automorphisms. That's true for any isomorphism. So if A and B can be swapped by an isomorphism, an automorphism, I would have to have the same degree between these 2 vertices, and I don't. A is of degree 4 and B is of degree 2, so it's simply not possible to find an automorphism that switches them. Since I can't find an automorphism that switches these 2 connected vertices, this graph is not symmetric. What we've come very close to proving, in fact, is that any connected graph, if it is symmetric, must be regular. Remember, that means every vertex has the same degree. We didn't fully prove it, but basically that's the idea. That if a graph does not have distinct connected components, okay, if it is actually connected, if it's symmetric, then any 2 vertices that are connected must have the same degree. But since the graph is connected, you can kind of walk from one point to any other in the graph, and therefore you would show that all vertices must have the same degree. The above graph looks symmetric. There's a visual way of saying, if I just move the vertices around a little, I could maybe split it with a line here and have a visual symmetry of the graph. But graph symmetry is not a visual thing, okay? Graph symmetry is about automorphisms of a graph, which has to do with bijections between vertices that preserves edge structure. Nowhere in that definition did how does the graph look ever come up. Okay, it is not a visual phenomenon. It's not something about how we draw it. Graph symmetry is a property of automorphisms and needs to be attacked through that language. Okay, so it is possible to find an automorphism of this graph that swaps certain pairs of vertices. If you construct an automorphism of this graph that keeps A where it is, swaps B and E, swaps C and D, then I did find an automorphism that does swap C and D. However, the definition of symmetric required that any pair of connected vertices must be able to be swapped by an automorphism. So just because one pair of adjacent vertices can be swapped by an automorphism does not make the graph symmetric. It has to be doable for every pair of connected vertices, and we were able to show that in this graph, there is in fact a pair of connected vertices that can't be swapped by an automorphism.